Okay, here's the second and last part, looking at Voronoi diagrams, just applying it more. And I'll get straight to it. I got a situation here in which the diagram shows 5 different water sources, A through E, as well as several, but not all, of the perpendicular bisectors. So a few things we want to do. We want to sketch the perpendicular bisector to enclose cell E. So I can see over here that cell E is partially enclosed, but it's definitely not fully enclosed because it and D are in the same cell. Determine the equation of that line that encloses it, and then make a sketch of the complete diagram. So first, just as a quick sketch, if I just look at cell E, I can see, okay, there's got to be some sort of line over here. That is the bisector, the perpendicular bisector between E and D, and I want to find that in detail. So the first thing I want to do is find the midpoint between E and D. And so let me visualize that. And in this case, I can see roughly it's right here. Now, if I look at my coordinates for E and D, you know, E is exactly at 3, 3, D is exactly at 4, 1. So that midpoint I can see must be at 3.5 and 2. There's the midpoint. Next, if I want to find the perpendicular bisector, it has to go through that point, but it has to be perpendicular to that line ED. So let me find the slope or the gradient of ED. So the slope of ED, I can just see from the graph, it's down 1 over 2, so it's negative 1/2. Sorry, negative 2. It's down 2 over 1. Classic mistake there, getting those mixed around. And therefore, the slope of my perpendicular bisector, I'm going to call it L1. I'll make a quick little sketch of it. Like I said before, it's something like this, right? That's what I'm calling L1. The slope of that must be perpendicular to negative 2. So it's positive, and it's not positive 2, it's positive the reciprocal of 2, so 1/2. And now I can find the equation of that line I've drawn in red because I know the slope and I know a single point. And so I can use, for L1, I can use the slope point formula or gradient point formula. In this case, the point I'm looking at is 3.5, 2. And it doesn't specify what form to put my equation in. I'll just isolate y. I put it in slope-intercept form. And so I get y equals, I'll decimalize everything for just because, why not? I get 0.5x minus 1.75 plus 2. So that equation that I've shown in red, actually I'll write it here in red, is 1/2 x plus 0.25, which actually from my little sketch, I can see looks about right. I mean, that line I drew, I just eyeballed it. But I can, if there was a big mistake with my equation, I should be able to tell, but my y-intercept seems to be accurate. All right, so that's the equation of the perpendicular bisector. And so now this region here properly fills in the cell for E, all the area, all the region in which all the points are closer to E than any other point. So now for the rest of it, I want to complete the rest of the diagram. Just sketching it, I'm not going to be as detailed as making sure every point is perfect. So first, let's visualize what's left. I need to have all the rest of my perpendicular bisectors. So for example, if I look between A and B, I don't have the perpendicular bisector for that. So from a quick sketch, draw that. The midpoint is roughly about here. The perpendicular slope, I mean, I can actually be quite accurate with this. The slope from A to B is up 4 over 1. So it should be down 1 over 4. So from a quick sketch, roughly like this. All right. And I need to find the perpendicular bisector between B and C. So again, I'll visualize that. There's the line BC. The midpoint is roughly there. The slope from B to C is down 1 over 4. So this should be up 4 over 1. So I don't know, roughly there. and I need to find the perpendicular bisector between C and D. Now, at this point, it's getting quite messy, which I appreciate. It's the midpoint is roughly there, and the perpendicular bisector is roughly like this. Okay, I got a lot of lines going on here. So first, let me start cleaning up and really grabbing my eraser here to be careful. I think I got all my perpendicular bisectors drawn. All right, so region E is good. Let me start to look at different regions now. So for example, for region, let's look between A and B. The bisector here must be part of my boundary, but then E comes into play, so I have to have these boundaries. Looking up at the top between B and C, this bisector must be the boundary between B and C. And again, I already have this for cell E. Between cells C and D, that must be this. I'll use this bisector right here. Again, this is complete. And then finally, I realize I'm not done. I never found the perpendicular bisector between A and D. So one more. This is actually probably the easiest one to draw because they are horizontal. They lie on a horizontal line, which means the perpendicular bisector is vertical. Right here. So there's a perpendicular bisector. But in terms of the region I want, it's this here. So now I'm going to start erasing, but all the dark blue lines, those are the boundaries I need. So all the thin black lines are the bisectors I use part of. And so this is a complete Voronoi diagram. Maybe I'll just highlight these boundaries first. Now on an assessment, you'd want to be careful not to completely erase everything else because essentially what we're seeing is all my work as well. But this is not an assessment, so just to kind of clean it up now, I have something that looks like this. There we go. There's my completed Voronoi diagram. All right, so on the back side, I have one question with a few parts to it. In this case, A, B, C, and D represent cell phone towers, and the coordinates of all 4 points you can see are there. As well, the region, that shaded region, shows the coverage of these cell phone towers, and each unit represents 1 kilometer. So I first want to find the area of the region covered by cellular tower A, which is this region here. All right, so I can think of this as a composite shape, and there's more than one way of doing this, but what I like to start with is I like rectangles. Area of a rectangle is quite pleasant, length times width. In this case, it's 2 times 3, so 6 square kilometers. This region here is a nice right triangle. So it's just base times height divided by 2. In this case, 2 times 2 divided by 2, which is 2 square kilometers. So the only part that I can't immediately figure out is the area of this triangular region here. However, if I imagine turning my page sideways, I can think of this part here, which I'll draw in green, this being the base, which I can see has a distance of 3 kilometers. All I don't know is this height from here to here. So if I can figure out this point, and if I look at the graph, I don't feel confident that I can know with great accuracy where that point is. If I can figure out this point, which I'll call E, if I can find the coordinates of that point, really just the x-coordinate of that point, once I know the x-coordinate, I can figure out how far that distance is from there to there, which again is at a right angle from the line I've drawn in green, and then I can find the area of that little triangle. So now I need to find the area, I need to find the intersection of that point E, or which is the intersection of several lines. I have several lines I could choose from. I want to look at this equation here, definitely, because I can see the y-intercept is at 5, and I can see the slope is -1, which means I can see the equation of that line already. I'll call that line 1. So line 1, I can just see the equation is y equals -x, because the slope is -1, plus 5. All right, I have now choose if I want to focus on this line here and imagine it going like this, or this line here. I definitely prefer the latter, this one like this, because I can see the x-intercept. And the slope, if I'm not sure what the slope is, it looks like it's 3. But I got to be careful. I mean, it looks like I'm going, it looks like it's going up 3 over 1. It looks like it's like this. However, I want to be a little more detailed. So to be sure the slope of that line in pink that I've drawn, well, that's the perpendicular bisector between A and D. So should be getting more routine. I want to first think about where's the midpoint between these. And that's the midpoint between A and D, which if I look at the coordinates of A and D, I can see the midpoint must be at 2.5 and 1.5. Okay, that's the midpoint of AD. And if I want to, therefore now, if I want to find the equation of that line, I have a point. And now back to the slope. If I find the slope of AD, if I look at the slope of that segment AD, I can see it goes down 1 over 3. So it's negative 1/3. That means the perpendicular slope of AD must be the opposite reciprocal, so it is indeed 3. So now I've confirmed that segment that I've highlighted in pink does have a slope of 3. I also know a point. It goes through 2.5, 1.5. So now I can find the equation of that. And so I'll call it L2. And again, I can use the equation, the slope point form. So in this case, y minus 0 equals 3 times x minus 2, or just 3x minus 6. Now in this case, I have two equations. If I want to find where they intersect, which is point E, I just need to find the solution between these two equations, which I can solve algebraically actually quite nicely. If I make them equal each other, I can quite quickly solve for x and y. I could solve them graphically, all of which are quite quick. In the end, I can see these intersect. So I'll say L1 and L2 intersect at 2.75 for the x and 2.25 on the y. So that is point E. Which is going to be helpful for the next question as well. And again, whether I solve this algebraically or using my GDC, it should be really quick either way. Now to find, again, the whole point of this was to find the area of that little triangle. So now I know if point E has a x value of 2.75, then I know this distance from here to here is from 2 to 2.75, so that's just 0.75. So therefore, the area of that triangle, I can figure out by saying the area of the triangle must be 1/2 the base, which I'm saying is the vertical. I'm thinking of this rotated, so the base I'm saying is 3 times the height, which I just figured out as 0.75. However I look at it, I should get the area of that triangle to being 1.125 square kilometers. So now, putting everything together, the area of this entire region is 2 plus 6 plus 1.125. And so I'll say the total area is 9.125 square kilometers. Clearly, there's other ways I could have found the area. I could have broken it up into different shapes, but that point that I found at some point that I needed to be really certain about what that intersection point between those perpendicular bisector is, what point E was, which is helpful for the next question. Because the next question, they give us the coordinates of this other point right here, the point equidistant to B, C, and D. I'm going to call it F. And I say that it's at 3.65 and 2.55. All right, so that's what's given right there. So the cellular provider wants to install a new tower to improve service in the region. They want to install a new tower at a point furthest from existing towers, which makes sense. Show the point equidistant to A, B, and D is the ideal location. So the question's telling you that this point right here, which is what we just found, E, is the ideal location for a new tower, which means that is the point that is furthest from all the existing towers. So how can we prove that? Well, if we just look at my diagram, and I'll clean it up slightly, And I'll get rid of this stuff for a moment. I know that point E and point F are equidistant from different points. For example, E is the exact same distance from A, B, and D, whereas F is the exact same distance from B, D, and C. One of those has to be the furthest, the best point overall. Because, for example, if I pick any point within a region, it's definitely closest to 1. If I pick a point just between 2 regions, it's going to be closer to these, but getting too far away from these. So we want to be furthest from all. It has to be one of these solutions. So the only question is E or F better? The question's telling you that E is the best, but how can we prove it? Well, if E is really the best point for a new tower, if it really is the furthest from all, then all I need to do is find the distance from E to A, or E to B, or E to D. They're all the same. Find one of those distances. And do the same thing for the other point. Find the distance from F to C, or F to D, or F to B. Those are all the same. Pick one. And if point E really is the best, those distances should be the longest. So I need to find the distance from E to any one of those points, and then from F to any one of those points. It really doesn't matter which one I pick. I just want to pick something that gives me the most pleasant numbers. So for E, I want to find the distance from E to A, just because the coordinates of A, I think, are quite pleasant, 1, 2. So how do I find the distance of that? Well, we use the distance formula, which is just really the Pythagorean theorem, which is a square root of the difference of x coordinates squared and the difference of y coordinates squared. So let's see that down here. So if I want to find the distance of EA, and keep in mind, I'm just picking EA over the others just because I like the numbers, the coordinates for A, 1, 2. But I should get the exact same thing for B and for D. And so that distance is going to be the square root of the difference of my x coordinates, which in this case is 2.75 minus 1 squared, and the sum with that with the difference between my y coordinates squared, 2.25 minus 2 squared. And evaluate this, and I get approximately 1.77 kilometers. So that means this distance from here to here is approximately 1.77 kilometers, which means so is this distance, and so is this distance. Okay, so now I need to do the same idea for this point here, F, to any one of the points. I'm going to pick FB. I'm going to go from here to here. Just because the coordinates of B are quite pleasant, 3, 4. So same idea. Let's find that distance. It looks like it's shorter. I can just from looking at it, it looks shorter than what I drew in red, but let's be more detailed than just by how it looks. And so let's find the distance of FB, which again, same idea. Looks more messy than it is. And I should get approximately 1.59 kilometers. And so now I can see, yeah, this point here is the farthest point. Therefore, the ideal location to put a new tower. Now, please don't think it's the farthest point. It's the farthest point equally from all the points. By that I mean, yes, if I pick a point here, okay, you know, the distance from here to here is definitely farther than what we had. But we want to find a point that is kind of farthest from all of them, kind of equally. And so our solutions for these will always be one of these intersection points between the boundaries. The question is, what's the ideal one?